We're going to live stream this lab as usual. So you're YouTubers now. Don't forget to put your Venmo. All right. Okay. Okay. Good morning, everybody. Today we'll do laboratory number 6, which is time series. So please go to your HydroShare account. Open the file called lab number 6 time series 2021. All day, isn't it? All day. Yeah. Well, one of the things that we don't like in remote sensing is snow, because or clouds, because it obscures the surface. We don't know what's going on, right? So, okay, so when you open your HydroShare account, or open the file lab 6 time series 2021. That lab is an upgraded version of what before geemap. Doing time series was very difficult. The other file called lab 6 contains a lot of code. It was possible, but we have to develop a lot of code. Now, but with geemap, we can do much more with less code. And we're going to use a couple of other tools called eemont. Eemont is a Google Earth Engine repository of vegetation indexes. They are curating a list of indices, not only vegetation in general, spectral indices for wildfires, snow, stress, chlorophyll indexes for water. So they probably have already over 200 indexes ready to be applied to Landsat or Sentinel-2 or MODIS. So today I'm going to show you how we apply that to an entire collection from the beginning of the Landsat data collection till the last date, and then how we can see all that data at the same time. Okay, there are a couple of ways to do that. And as a bonus, how to get that data out. Probably some of you have worked with pandas, Python pandas, and you can work on tables. So we are going to get the data out into a pandas table. And from there is much easier to manipulate the data into statistics, plots, and such. So we'll do that. So what is everybody here or still waiting for HydroShare to load?
The server's starting.
Okay, right. So if you already have this, open a terminal. But in this case, you need to run these three commands. Pip install eemont, pip install gtools, pip install minus capital U geemap. How's your term project going? Yes, I'll need to attend that.
Yeah, I'm gonna have to figure some things out too.
Okay. Right.
Yeah, it's still okay. Sending results. Decent start.
Okay.
A lot more to do.
All right. All right. Okay. Yeah.
So, good question with the project. Can we just, if we hit a black hole, just change the idea a little bit?
Say that again.
Can we make changes? Because we submitted the idea.
Oh yeah. I
Okay.
mean, it's like any research project.
Okay.
Okay, you propose to do something. Let's say the data is too complex, or you plan it to run, let's say, 30 years worth of data. You don't have the time. You need to run only 5. It's okay. It's okay. Because I know you have to code, or you have to think about what function can I use, and that is also a learning curve. Okay, so can be flexible on that. The thing is that after this class, you have some experience coding, which is very valuable nowadays when you go out and you say, yeah, I used to run code on Google Engine. Oh, okay, that's interesting. And yeah, Google Engine is becoming more and more accessible because of the library that we're going to use today, especially the eemonts and geemap. Those two. G-tools was an early package that helped us to do some stuff, but I found that geemap and eemont are more useful for the activities we're doing in this class. Okay. Who is ready? Still waiting?
I got open, I'm installing the packages.
Okay. Okay, let me know when you're done with installing the packages.
Six, sorry.
6, 2021. The other one is the early version of, has to say 2021. This is a good question for you. Who is staying for the summer?
For summer?
Yeah. Who might have some free time? Well, some free.
Says how much free time.
Well, it's a paid free time.
How much paid?
Well, it depends. No, what I'm thinking is I have ideas to upgrade this class. Okay. So what we're going to do is some of the early laboratories are going to become more ArcGIS Pro friendly. And we will keep, for example, the time series maybe can be done in ArcGIS Pro and maybe can be done still in geemap. But the good thing is ArcGIS Pro now speaks Python or Jupyter notebooks. So instead of running it in HydroShare, it will be run from ArcGIS Pro. So I have ideas for upgrading the material, and I could offer an early stipend for that. So after the semester is over, you see your times, let me know if you're interested, and we will work over the summer to upgrade the material. There are tutorials, there are material that I have that I want to change to make this class to progress faster. Okay. All right. So is everybody there? Okay. So next, once you install the notebooks, run the first cell, the one that imports all the libraries. Look that in this time, we're going to call pandas, NumPy, Seaborn is for plotting, and Matplotlib to generate the figures. Okay. Now, because it's Friday, and you know what happens every Friday, right? We need to get the code. So run that cell. In my case, I just did it before class. And if you get a requirement for that, you can just complete that part. If you get a map like mine, then you're all set.
We have something,
What?
do we have something? I have run this,
You got it?
yeah.
Okay. Who got it? Okay, really good. Okay. Now, okay. What we're going to do now is we are going to locate 3 farm spots or 3 farms in Utah. I already pre-selected these ones, but we could change it if we wanted. So remember last time we were drawing geometries and we had EE geometry polygon? Yes, and we had to enter 4 corners, right?
Yes.
Another geometry is point. And in this case, I'm looking for 3 center pivots, these circular forms. So to describe a circular geometry, you need a center coordinates and a radius. So with these 3 coordinates and the radius, I can describe the geometry of 3 center pivots. So you can run that cell. So now they are plotted in a black color. That's something I didn't like much, but 1, 2, and 3. Okay. In this section of the code, look, I create the geometry for each of them, pivot 1, 2, and 3. I add those geometries to the map add layer, pivot 1, 2, and 3. But also, instead of me entering a coordinate to zoom in, I can select one of the pivots. I'm saying map, center object, pivot, and a sub-level. Okay, if you got that image, great. Now, it will be easy to get information about just one center pivot. But let's imagine you're managing 100 center pivots. Okay, so let's say we want to get a time series of 100 polygons. So in that case, we need to combine these center pivots into one, let's say, into an aggregated variable. In this, Google Engine allows us to do that by saying feature collection. So every pivot is a feature, and we're creating a collection. So by passing that command, I combine them, all of them. Okay. So now I have a variable called generically pivots. Okay. And inside that variable, I can have as many polygons. I could have in these features means vector data. So I could have polygons, I can have rectangles, center pivots, points inside that. In this case, I'm filling it up with only 3 circles or 3 circle features. Okay, but each of them is identified by a name or a class pivot and a sequence number 0, 1, and 2. So
It's kind of merging.
it's like merging by keeping its own properties. Okay. Now, who likes snow? Well, if it's Saturday in the morning and homeworks are done and the midterm exams are passed away, right? Yes, it's fun because you can go up to the slope, it's sunny, you have plenty of snacks and your friends, and that's a perfect day. But if you are going to school and the roads are slushy and slippery and you see a crashing main street, yeah, it's not fun. Okay. So neither do we like in remote sensing, unless you're studying snow, then it's good. But we don't like much snow. So we're going to create a mask that will filter all snow pixels. Remember the spectral response of snow. What's the characteristic of that spectral response of snow? What was the shape?
For the symbol RGB.
Yes,
And then
flat, near infrared 2, and then it drops, right? It's like bouncing, the signal was bouncing until at 2.5. Pretty much every signal disappears at that point from every land surface. The signal disappears. So what we're going to do, and this is an index, there is a vegetation index to detect the snow. It's called the normalized difference snow index. Okay, so this index is going, which band is using? Look, this is Landsat 8. So it's blue is number 2, green is number 3. So it's shifted to one value. Okay, so this is 3 minus, this is green, and this is near infrared. So it's doing an NDVI with green and near infrared. But look at the order. The order is different. Okay, typically when you do NDVI, you put first the near infrared and then the red band. In this case, is the green band and the near infrared. Is the near infrared? No, sorry. This is 5. This is a short wave band. Let's look where is our one now? Let's have that clear. Okay, where is my? There we go. So what it's doing is this vegetation is saying, let's take green. Okay, it doesn't matter if you take blue or red, they are the same value. Okay, and then let's take a short wave. 1.4 is taking this value. Okay, what it say is that this is snow is going to be high in these values in the RGB, like fresh snow versus 1 day old, 2 days old. It start getting less brighter, right? Like as the days go, because it start melting and refreezing, melting, refreezing. Start the particles in the air start falling in it, so it's not as white as the fresh snow. But this value is going to change very little. So this is our anchor point. But this value, this is going to be moving like crazy. Okay, so in this case, we're going to use these two to calculate the occurrence of snow. So what is saying here, let's take the band number 5, band number 3, and let's calculate the difference. Here is, yeah, let's calculate this normalized difference, but also let's have the near infrared band here in the green band here. Okay, because so what it's doing is I calculate that normalized vegetation index, but I'm going to say the snow pixels are the ones who have a normalized vegetation index larger than 0.4. Okay, I'm separating. And the near infrared value is larger than 0.1. And the green value is larger than 0.11. So what I'm doing here is I'm adding more conditionals to my filtering of what is the snow or not the snow pixels. So by doing this, I'm saying, okay, now I will have an image that has zeros and ones, it's a mask. And now from that Landsat image, update mask the opposite of those pixels that were detected. When I put this symbol in Python code means the opposite. If I have a mask that is zeros and one, what I'm selecting are the zeros instead of the ones. So this is a function, okay, in Python, but for us to process every image in, let's say, that was collected by Landsat 8, I need to create a function that will be iterated over every single image. So now that we have our mask snow function, the next step is to call Landsat. So we have here an image collection, Landsat number 8, process tier 1 surface reflectance. We're going to filter bound the image by the pivot feature collection. Now, the good thing about eemont is that it has this option, mask clouds. In the past, we have to create a function like the previous one to mask the snow, but now we use, if we call eemont, we can just say dot mask clouds. At that moment, the internal, the additional information in other bands of Landsat become available to determine if any pixel has a cloud or a shadow of a cloud on in that position, so we can get rid of that. Then also we say scale and offset. if our data is not like remember when we had to multiply by a value and add a constant to transform from digital numbers into a 0 to 1 reflectance? The eemont, instead of us doing that, we just pass the command scale and offset. The eemont package takes care of that, goes into the metadata of the satellite, the information, extract the values, and it will apply the correct values to transform the data. It will work for Sentinel-2, Landsat, MODIS, so we don't have to check which values we need to extract. eemont take care of that for us. And one more thing, we can tell using the eemont package which spectral indices we want. I want NDVI, NDWI, and GBMI, just to give you an idea. But what are they? And finally, map or iterate the function that I created to detect the snow pixels. So they will be masked, they won't show up in the image.
Can you explain again?
Okay.
Scale and offset what?
Okay, the scale and offset. Remember that we do Landsat A is equal to Landsat A dot multiply. We have a value here like 0.00032, something like this, dot at minus 0.2. Remember we did that several times?
Yes.
Okay, instead of us doing this, if we call the eemont package, we just say scale and offset. So instead of us doing that, now is Landsat A dot scale
And offset.
and offset. Offset. These two are the same.
So some of satellites, some of bands, the equation or the value is not the same.
Yeah, because these values are for Landsat A. Landsat 9 has its own values. Sentinel-2 has its own values. So
it goes by.
yes, but the good thing is if we use eemont, if we have Sentinel-2 dot scale and offset.
The program just knows what to scale and what to offset.
Already, yes.
Yeah, it was.
Okay, so we don't have to memorize or look into the metadata. We just need to pass this function and we're golden. Okay, so that's why I leave you on the very top.
And if there's an image that doesn't need scaling or offsetting, or does not do it.
All images require, well, the one that doesn't need is naive, because naive is from 0 to 255, but it's not reflectance. All other images require scaling because trying to an image that store decimal values in the pixels takes more hard drive space than an image that was multiplied by a factor. Like you take an image, multiply by 10,000, the entire image, okay, and then convert it to. Have you heard about this? U8, 8, U8, 16, U8, 32. Vote. Okay. What is this? This is telling you in which number format the data will be stored. These three will accept only integers. Note that these accept integer plus decimals. Okay, so here all satellite data is stored here. for archiving, but the analysis is done in this. So by us scaling, doing the scale and offset, we transform the data here, there. So, but the reflectance data has to be working this way, but it's stored this way. So Landsat 7 used to work here. These integers go from 0 to 254. You in 16, what does it mean? This 16 is 2 to the power of 16. You intend to, so this is the maximum value that can go in this scale, from 0 to this value. So this is 2 to the power of 16 and 2 to the power of 32, but integer. So we always work here. All our analysis is in float or DOM. But these are heavier. It could be the size of the file could be 2 times the size of the file here. So for a matter of storage, all the image data in the NASA archives, in Google Earth Engine, in Amazon Cloud, it's here in UINT form. We need to transform it into float or DOM. Does that help? Okay. So a scale and offset makes the work for us. Mass clouds. Every satellite image has an additional layer that has information about if a pixel is affected by cloud or shadow of a cloud. The eemont toolbox or package reads that additional file and apply the mask for us. And once we do that, once we have a scale and offset the data, we can ask for indexes, for vegetation indexes. And what are those indexes? I left you a link there. And this is the what platforms what platform eemont supports: Sentinel-2, Landsat 8, 7, 4, MODIS, Aqua, Terra, and here are the database of the indexes. Blue, normalized, different vegetation index, low chlorophyll index, enhanced vegetation index. So if you find a study that says, oh, you're going to start aquatic environments and you need to apply a chlorophyll index, then you can just call with these 3 letters, you can call that index into your calculations. Here, you just say dot spectral indexes, and you can put as many as you are interested on. And finally, we filter the snow. Okay, so let's run this. Oh, first let's run the mask snow. The eemont list of indexes is there. If you run it, it has over 200 indexes already. It's just amazing how creative humans are. Okay, now let's check which bands are available for our calculations. So from my Landsat 8 image collection, I have these bands under these names: B1, B2, B3. Here is the information about pixel quality. And look at the very end. Now we have NDVI, normalized different water index, green vegetation. I don't remember the index. So now, just passing that previous function, we have our vegetation data or our index data. Okay, so now let's
let's see visually in a map how the NDVI changes in a map over a year of data. So here let's put a more recent year in the time lapse of satellite data. Let's put from the 1st of 2022 to the end of 2022. So what it's doing here is in Landsat 8, I'm going to select the band NDVI. I'm going to filter it by the date, and then I'm going to sort it by just in case I'm sorting it by the time when the satellite was acquired from the beginning till the end. I'm going to create a color map that goes from light yellow to dark blue because I'm looking at NDVI.
And I try to run on
Oh.
0A.
Yeah, I got an error too. Parameter image is required. Parameter image. Oh, first image. No, we have run everything to solve. Oh, yours is a token, right?
Yeah,
So token means
I run from 0A from geemap. By token, but it's still at the same level.
okay. Let's try this. Kernel. Yeah, restart kernel and clear our outputs. Restart. Okay. Since we're already in this cell, click on that cell, go to run and say run all above selected cell. It's working now for me. Let me see. Image parameter. Let me see. I got the map. Okay.
Which line you got here?
I got an error in
Which
map add layer first image.
works for me, don't give me an error.
Can give you an error now. Does it work?
It didn't work for me either.
But it works for me.
Okay.
Maybe it's-
Worked for you?
Yeah, for me too.
Worked for me. I just had to restart it. I just worked off.
This work for you?
Yeah, it worked the first time. I don't know why.
You have you asked it first before that for the token or something?
Yep. Because I came early, I was running the exercise and everything was just working fine. Okay.
You're right now using the same.
Yeah, we're not changing code. So,
Yeah, that worked for me
oh,
too.
okay.
Change the date.
What's the date maybe? That's the only thing I changed. Let me see. Okay, 2021.
Work now.
What's wrong with? All right, it works. Okay, so what is plotting? I'm asked from the collection. With the collection is all the NDVIs in order. Okay, from the first day the Landsat camera was working, or from the 1st of January to the end of the year. This is the first image. Of the NDVI. What do you think are the empty spots in the image? It's not complete.
Snow.
Or clouds.
Or clouds. But this is the north part of the image. I can believe it has snow. This is Utah. We're in Utah. And here are our three center pivots. Okay. And so this is St. George is here. So the image is expected to have the minimum amount of cloud, no, snow in January. It's pretty much in St. George doesn't snow. Okay, but here is the Wasatch Front. And here we expect to have snow. So clouds and snow have been removed from my NDVI image. So then we didn't have to do much work in coding. That's the beauty of functions and libraries. Okay, so it looks like this. All right. Now, but I already have the entire archive of NDVIs, right? So let's do this. Let's go to the range toolbar, go to the views, and turn off the first image. Okay. Now run the next cell.
You turned on, oh,
Yes. All right. All right. Guess what we have here now? Now we have a way to see every image for that location. Okay. So if you zoom out enough to see your entire image, okay, you can click play.
so what is this going through? How many, what's the point of these images from again?
This is 2021 from the January 1st to December 30th.
It's just like once a month or?
Landsat date, yeah, it's every 16 days. So we have,
Every time there's a new. Every time there's a new. image.
yes. Isn't that cool?
That's cool.
Yes. The location we selected is exactly, and this is another tip about satellite data. I always give you the tips. When you have a satellite data, okay, it always overlaps a little bit with the next one. Okay, this overlap, okay, and the three center pivots we have happens to be here. That's why it's calling when we tell, hey, give me this Landsat data based on these filter bounds. It say, oh, these guys, this location and this location too. So that's why we have two images. Some images you see that is pretty much no NDVI at all because everything is cloudy.
Yeah.
And other days, you have almost a complete Landsat image. So that's the nature of satellite data. It's not always perfect. That's the reason we always want more. We always want more frequency of data. Because as you can see, this one, we're missing a lot of data. Other cases, we have entire image. It's not always good conditions. All right, and now it's cycling back again. Let me put a pause. Okay, so that's one way to see the image. Geemap has an option. Geemap, one of the notebooks, shows you how to create from this sequence of images a GIF. Like, have you seen those photos that changes? Yes, it can create like a tiny movie of your sequence of Landsat data. Okay, now that we have our data, now it's time to look at the center pivot's performance. Or how was the NDVI for all the Landsat dates over those three center pivots? So we have a function in geemap called get time series by regions. Regions are going to be every center pivot or every polygon we have. So it's going to ask us what's the collection of features is the pivot variable. Which bands what I would like to, I could put here the blue band, the green band, or vegetation indexes band I already calculated. And what is the statistic that I would like to get? I would like to get the mean value, the maximum value in the center pivot, the minimum, the median, quantile. So it allows me to select which statistic, in this case, use the average mean, I would like to get. And what's the pixel resolution I want this analysis to be done? Landsat, it's at 30 meters. So let's run this cell.
So you take the average between which bands, NDVI and
For every band.
uh-huh.
So you have you have your image of NDVI, you have your center pivot, it will take the mean value within the center pivot.
So you give us just one number
Per image.
per image.
And we have a collection.
Yeah.
Yes. So in the variable TS, now we have the list, date, and the mean value of NDVI, NDWI, and GVMI. Let's convert that into pandas. Geemap, again, one of the interesting features about Geemap is that allow us to get this information, which is in a language called JSON. Have you heard of JSON? It's a sort of machine language to store table data. So it's called by this is the format JSON. Okay, and the data that is extracted from this analysis here is stored like this. It's kind of very unreadable. It's well structured for an algorithm to read, but for humans, it's very complicated. So we have a conversion here to a pandas format. Let's run that. And now let's see the table. Can we identify for which center pivot and for which day each spectral index was value was calculated?
For me, the drawing.
Okay.
Yep.
But look, what does it mean? This minus 999. Yeah, the cloud or the shadow pixel, because this location doesn't get the snow. This is way south of Utah. Question? Okay. Okay, so we can see that for the first image, okay, which in this case, one of the things that I need to mention to you, what we plotted in the map was only 2021. But what we calculated here, okay, was the entire archive of Landsat 8. So that table goes from the very first day, 2013, okay, 2013, all the way to 2021.
Data of 22 is still not every.
Though I think what I called not the, so the image collection of Landsat 8 that I call in the code is not the most recent one. They have been updating it. It's still there in the archive. Here, this one, I think this is, no, here. This,
Yeah.
this is an old one. And this one only has data until 2021. So if we go to
Yes.
Google Earth Engine, Landsat 8, surface reflectors, this is different.
Okay.
That's the reason the code failed when we tried to do 2022.
Why was that? I missed that.
Okay. So here, when we call the Landsat archive from Google Earth Engine, this code was valid in 2021 when I created the notebook. Okay. But recently, NASA has upgraded their processing of Landsat 8 data. So this code now is different. Google Earth Engine still keeps a copy of this previous code. That's why the notebook runs, but it only runs until 2021. When we try to run 2022, fails because there is no data. So in order to have 2022 data, we have to update this value.
Okay, that makes sense.
Is it supposed to take a long time for the table?
No, look.
Yeah.
You can interrupt the running with the square icon if it's taking too long. And try to run it again. So now we have a pandas table. They were in traditional Python world. Still running? Okay.
Shouldn't taste too much same. I think yes, we start the kernel again and
You can,
but still is next one.
yeah. Okay. If you got the table, who got the table? Okay, you got the table. You can be running the next two cells. First, we're going to get rid of that minus 9,999 value and put instead of that the non-a value, replace it by non-a value, not a number value. In that way, when we do our plots, we don't have a stretched image. So run that cell and then run the next cell. The second line, what it's doing is detecting the column that describes the time tell pandas, hey, this column that you have in the table is time. So pandas by default, who has worked with pandas before? Okay, pandas is like an Excel. Okay, it's really powerful. You can do figures, scatter plots, you can do regression analysis between columns, you can merge columns, you can split rows. So it's an Excel in Python version, but it's dummy. Dummy in the sense that it doesn't know what is here. So here we can see that it's dates, but pandas doesn't know its date information. So we have to tell pandas, hey, this is here in this row, we're telling, hey, pandas, that column called date is date. So recognize it like it's like Excel. Like Excel is slightly smarter on that. You put dates on a column, it start inferring it. Okay. So, but at pandas, but that's the powerful thing about pandas. When you tell date, you start specify a column to be a date. At that point, pandas become extremely smart because you can select periods of time in pandas that you are interested on. So you can select like only data that happened on May 18 of every year. So you can do this filtering of data or subsets of data based on dates. So why we do that? Because it's going to help us with plotting, which is the next cell. Now, I found a function that is called melt. So if you have used pandas, have you used melt? Okay. Melt is a function. Let me show you here. I have the same 3 dates here because they are the same image. Build 1, 2, 3, and I have the reducer and the 3 values that correspond to 3 center pivots. Melt will reorganize this table to make it more understandable. This is good, but just for fun, I said, well, let's reorganize the data. And we can check how it looks like. So I have now on the top part of the table all the NDVI values. After the NDVI values are all the green vegetation index and then all of them. So instead of having them 3 columns and this stays repeating all over time, it doesn't affect the calculations. It's just reorganized. Okay.
For one day, I'm looking for this function because I wanted to use it for seaboard. I know how you like simply for seaboard and works. I didn't know this function, so I tried another way to make this kind of thing.
Yeah. So, okay. Now that we have our table, now it's time to plot it. Now, to plot data, in, especially when you have multiple variables and you want to do subplots, it requires some code. So in this case, we're going to run this function based on the Seaborn package. We got our titles and we got the values, the vegetation indexes, the spectral indices, and how these values are changing over time. Isn't this fun? So the entire archive of Landsat 8, you just process it for 3 regions of interest. Okay, what can we tell? How is our time? 9:32. Okay, yeah. All right. So who can tell me what's growing in each center pivot?
Alfonso.
Which one is alfalfa? Is the right answer. Now I'm following up with.
Yeah,
All right.
I don't know, the middle one.
All right.
I don't know.
All right. No, you are right. Is okay. Which one is alfalfa?
I think it's the second.
The second one, pivot number 1. The one is called. All right. Well, this is part. Remember when we were looking the phenology cycle of a crop and how the NDVI can track that phenology? Like there is no vegetation, rapid development, floration, fruit formation, harvest, grow again, floration, harvest. Okay. So this is what you're seeing here.
During the years, takes for the 5 0, the first year, it's like.
Yeah, because you have so many years here, and the farmer is a smart person. Okay. For example, alfalfa, you can run it only as a maximum of what, 6 years? Yes, about 5 to 6 years. After that, you get low quality alfalfa, so you replace it. Okay. Also, if you are cultivating corn or small grains, you can run up to 2 or 3 years, but after that, the fertility in the soil declines, and a natural way to refill or restore the soil fertility is by planting alfalfa. So what you are seeing is the evolution or the changes that the producer made over the year when planting crop. In this case, let's see pivot number 0, the first one. This is not alfalfa, but these ones are. This is alfalfa, alfalfa, alfalfa. This might have been alfalfa. These two aren't, but there are 2 cuts here. Okay, so it might be early alfalfa, planting alfalfa. Then he went, and this is, I know because I've been around this area. This is corn. Okay, corn. So it's just one major grow and cut. So here, what is this early in the year grow? What, because in this place that there is no snow, anything, wheat. So there is no snow, but there is rain. So after the alfalfa, no, the corn is cut, then wheat is growing. The farmer has to tilt it and then plant the corn.
The months started from January to January.
Just, yeah, here is January in these little icons here.
Okay. Sure.
The second one, it seemed that always was alfalfa. It's still alfalfa because of we cut alfalfa 4 times per year. So when you see this variation, we're seeing alfalfa. Look at the magnitude of the values, the peak, because remember, these are the mean value of the center pivot. Are they close to 1, the peaks? What does it mean for us? You are a specialist reading NDVI. What? Yeah, they're very healthy. What was our threshold limit? NDVI. Healthy. Below that, issues or in development. Below 0.3 and dBi below 0.35 soil. So there are moments where the NDVI is low, and those are the early in the year moments. And at the bottom on center pivot 2, alfalfa, another crop, and then we go back to alfalfa. Now, NDVI is the blue line. Okay. Then we have the GBMI. Let's Google it, shall we? What is that? GB. Okay. Google says this is the global vegetation moisture index. Is suitable for retrieving vegetation water content when the LAI is equal or greater than 2. So there's the GBMI. The second is the crop water stress. So let's try to interpret GBMI. GBMI, we're being told, it's telling us it's an indication of if the plant tissue had a relative indicator of plant tissue moisture or content of water. So in a sense, you can relate it with the stress. Less water in the plant is more stressed. In alfalfa, we see that the GBMI index follows pretty close the behavior of NDVI, but it never reached its maximum value, right? So nevertheless, the values are high, all aspects. And this is because, especially for this location, I know the farmers irrigate every 4 days. So they're keeping the plants, I mean, he's not taking any chances in yield loss because this is a milk production facility and they have to be producing hay, alfalfa hay and corn hay or silage corn for the cows that they have. So the moisture also is telling us the crop during the growing season is doing well. Here in the low vegetation period, the article we're pulling up from Google, from Google says that we cannot interpret it well. What is the other index? Normalized difference water index. Let's double check. Normalized difference index. Okay. Normalized different water index. The NDWI measures moisture index and is compared to the normalized different moisture index. Okay. So what it's telling us is an indication of moisture. So again, it's telling us now, but it's telling us moisture in general. Okay. So if we align the peaks of the NDVI with the peaks in soil moisture, we see that overall, this is telling us that yes, there is a high level of moisture. I'm trying to align the peak of this orange line with the peaks of the NDVI. But what I want you to look now is when there is no vegetation. the NDVI is low, but the index, the water index is high. What does it mean?
This is in the winter, so soil moisture has high, has a lot of water in the soil,
Why?
Your plans.
There is no plant,
and also we got a lot of precipitation.
precipitation, rainfall. Because, yes,
WI.
because the index, let's look at that's a good question. Let's look at the formulation. It says for Landsat 8, band 3 minus band 5, band 3 plus band 5. Let's look at the numerator. What is band 3? Green. Band 5, near infrared. So it's like a green NDVI. But if we look at a plant, the band 5 is NDVI, right? How is the shape of my vegetation, spectral curve for vegetation? Which is higher, band 5 or band 3 in my vegetation spectral signature? But how is the subtraction done here? Is the order of the bands that is causing this negative. This is higher, so the values will be always negative. That's the reason in our chart, it's always, all of them are in the negative. So if they try to get closer to 0, so instead of us reading minus -1 better noise, the closer to 0, the higher the moisture. Okay, so by looking again to the early season, you see that the NDWI reaches its maximum. This is soil moisture. It's indicating that the soil is very wet, very, very wet, and the index is able to recognize that. Fun, huh? But there are years, let's look at this. It's not always here. It seems that peak is almost constant, but here we have a high peak, lower, lower, high, lower, lower. Something is happening here, up here, but these years seems to be different. Okay, fun. So in this code, you could change for any vegetation index that you find interesting. We have a massive list, right? Here in the eemont, we have a massive list of indexes. We have snow indexes, drought indexes, kernel indexes, so mathematical transformation of the data. Okay. Let's see temperature, because we can also do the same analysis now. This is band 10. Let's convert it to a table. Let's convert it to pandas. Replace the value. And let's plot it. All this temperature is in which units? The temperature, in which units it is? The range is in the 300s.
Kelvin.
Yes, very good. So what you are seeing is the variability now of the temperatures of the crop during the year. Now, what do you think is happening here? Why I have a spike? Or a drop?
The drop, like, the image was taken right after you went.
Yes, but it is rare that reaches 2.7. So this, despite the best effort, this is a cloud pixel. Okay, when you see a very massive drop, like you don't see it in the pattern. These are irrigation events. But this one has to be like frozen water. Okay, and frozen water in the summer, yeah, unless he's bringing from the fridge, right? And now, but now this is a cloud pixel. Other than that, this center pivot looks good. The first center pivot, these two might be clouds too. And these, I'm not sure. This might be an error in the image, which is rare because this is a spike of 20 degrees above a typical temperature of water. So that's very rare, very, very rare. But this also is an outlier. But we see the variability of between the growing cycle and the cuts, the variability of the temperature. We see the minimums that the soil temperature has. So for people that are studying stress, for example, there is a famous equation about the stress. Crop water stress index. This is not a remote sensing index. This is an agronomic index. Okay, who is in the PSC department? I know this teaching. Welcome to the department session. What's the question?
Water use of the water.
No, this is about temperatures of plant. Okay. Okay. What it says is if I know the temperature of the crop, I know the temperature of the plant, and I have what is called the baseline, two temperatures that define levels of stress, I could calculate an index that allows me to know if that plant is having an issue regarding water. There is another version of this equation. I mean, indexes, yeah, the people from agronomy are very, very creative. Are also say T crop minus T min, T max, T min. This is another way. So T crop is the T from the satellite. So if we knew these two values for alfalfa, we could transform these temperatures into an index from 0 to 1 and indicate in which moment during the growing season this alfalfa was under water stress. Okay, so from this groundwater stress, it is not a vegetation index, it is an agronomic index. Like you can have these temperature guns and go to a crop field, shoot it, measure the temperature there from the weather station, have this from literature and calculate. So that's what consultants do. They went in agriculture, there are consultants, people that goes and visit your field and give you advice. So one of the advice they give you is about how to track stress in the plant. Farmers know it due to experience and years of looking at the plants. There are ways to do it numerically, is with thermal sensors. So these infrared thermal guns are pointed to the crop with the temperature of air or information of a range of temperatures of which the plant should be, that demonstrate that is not under stress. We can calculate an index. If it's 1, is closer to 1, no stress. If it's closer to 0, it's under certain level of stress. So that this time series will, if we had that information, will allow us to see which moment during the growing period the alfalfa crop was under stress, or the corn. Now, pandas allow us to evaluate different tables. We can merge tables. We have a table for NDVI and we have a table for temperature. Can we merge these two tables based on the dates? Yes, we can. So we're going, the following cells are about merging those tables. Okay. With temperature. Once we merge them, we can plot one versus the other. Let's see, where is my plot? What do you see? Is there a relationship between temperature and NDVI? What's the relationship? Is linear, nonlinear?
It's not a very clear relationship.
Not very clear, right? Okay. This is because we're plotting all the data, including the winter months, when we don't have vegetation. But basically, about here, all these points are winter. Okay, it will left us with this point. What do you see there now when you eliminate these points? What's the type of relationship? It's a kind of like this, right? This is the fundamentals of what I do. This is the triangle method. Okay, I can pass a hard line here. So high NDVI, low temperature. This is maximum ET. any plant that has well developed, okay, and its temperature is low, that location is showing a high level of water being transpired by the plant and the soil. Low NDVI, high temperature, minimum ET. Okay, so this triangle method is the fundamentals for calculation of this variable called ET. And basically is like, say, this is going to be, let's assign, so if, how to assign the value? We're going to say this is close to 1 in ET and this is close to 0. And the idea here is to interpolate. So this is 0 and NDVI is still 0. This is 0. Okay, we're going to calculate a 0.5 value here. Okay, between these two extremes. This will fall into T at 0.5. I should use another one. NDVI at 0.5 and T at 0.5. Okay. All these values are going to have all these combination of NDVI and temperature pixels will have, there will be midway between the minimum temperature and the maximum. So basically it becomes like this, ET or a scale of ET will be in function of temperature and NDVI. So based on the combination, so I'm going to say if this is 0.9 and the temperature is 290, right? 290, going to assign this maximum value, and if the temperature is, the NDVI is 0.15, and my temperature is 318, I'm going to assign it close to 0. So what I'm going to do is, in the image, I'm going to start looking, I'm going to look for I'm going to develop basically an equation. I have this value and I have this value. I can develop easily an equation here, right? So what I'm going to say is that every time I am under this NDVI, they're going to have this same value. This NDVI going to have this value. So I can assign a ET range to every pixel in the image. This is the oldest, the oldest methodology that was developed to calculate ET. Is still used. We have refined from this because what it gives you is a sort of a scale, but it doesn't tell you the actual magnitude. It's telling you that this is low, this is high, this is the highest you can get. And with this shape, basically this line here, forget these points, but this line here, that's your range of ET. That will happen. Yeah.
I'm probably just thinking of it wrong, but for some reason, for me, it's counterintuitive to think that at high temperatures, you get low amounts of evapotranspiration.
So it is the combination high temperature, low vegetation. So
Okay.
it has to happen both. So
Okay.
you can have high temperature. Here we have still, I mean, we go few degrees, we're still hot, but high amount of vegetation. It's transpiring.
Okay.
But as the vegetation decreases, remember our rule below 0.3, we're in bare soil. So this soil, if the soil is hot already, it's because the water already evaporated.
Okay,
The temperature of the crop, or just the temperature of the pixel?
The entire pixel. So it's a combination.
But if it's, the whole picture is a crop, like.
Yeah.
The canopy is completely full, pretty much.
Is the temperature of the crop. If your fractional cover it's 1, then it's the temperature of the crop. But this is the most basic, the most fundamental, like as you said, but it has to be in pairs. It cannot go on just alone. High temperature, low NDVI, ET towards 0. Low temperature, high NDVI, ET is the maximum value.
In case that we have like high in DVI, we like to probably like vegetables.
Yes.
Like we don't irrigate it very well, then the temperature should be high.
Say that again.
Okay, if we have like in the field that we have like full of the covering of the
Yes.
vegetation,
Uh-huh.
and then we are not irrigated at all.
Yes.
So the temperature should be high.
The temperature, yes. So you see this flat area?
Mhm.
That's the fluctuation of your NDVI. Look, it's high, but also can be hotter. This is your stress. Okay. You have a, look, all the NDVIs are 0.9 here.
Yeah,
But your temperature, look, your temperature is changing. Here, the coldest, this is your perfect ET, but here is not that perfect.
it means you have some.
We have some level of stress. That plateau here, that variation there is explaining that.
Time goes after like 1 week, it will impact the NDVI also. I mean,
Yep, it start
comes
dropping.
down.
Yeah, it can start dropping. So basically, for that exercise, we could download the pandas into an Excel. For example, give it a color per year.
Mhm.
Certain points belong to 1 year, other points belong to another year, and see if this variation is because of the years or it's because of the changes in irrigation. We can, so similar, we can keep doing more plots. Now, this is the inverted index. Temperature versus moisture. How do we read this? What did we learn about moisture index? Or what do we know about the moisture index? We can filter again by our rule that anything below this value, it's winter time. So let's forget about these points. The lower,
That sounds good.
but remember, so the lower, we have a low temperature, okay.
And the NDVI has the highest.
So what is telling us is, what is telling us?
About the eating.
No, about the index itself. Is there any correlation between the index and temperature? Because it's measuring moisture.
Where is NDVI? It's so low, it means we have a lot of water in the soil, so the temperature should be low.
Yes.
And where it goes, then that the value increase. So
When the value approaches to 0,
Yeah, so
okay,
it means we have less water in soil and then the temperature would be higher.
yeah. The last one is this is just the previous one was a moisture index in general. This is for the vegetation index, more moisture index for vegetation only.
Sure.
And again, let's forget about these points.
So. Since where the index is higher, the temperature is lower, which is when the plant has less moisture.
It's the same figure as the first one, isn't it?
Yeah, like the
17.
NDVI,
Yeah,
it will have a similar behavior. The lower the temperature is indicated that the moisture of the vegetation is high.
high.
But as the temperature increases, we see basically a linear reduction of it.
Just can have chemical transpiration.
Yeah, it cannot transpire more. All right, yeah,
I have a question that goes back to like the very beginning, when we set the buffers for the
oh yeah,
center points,
yes.
are those values, is it 500, 300, are those meters or pixels? Or
Oh, meters,
meters?
meters, yes.
Does center pivots are like 1 kilometer diameter?
Yeah, but they're smaller than a mile. A mile is 1.3 kilometers. So these are small. But these are large pivots.
So I was thinking about using this on the East Coast, but it'd be really hard because a lot of those fields are not. The majority of fields on the East Coast are not that big.
I mean, you can use the polygon technique we used last time. And here in the geometry, you say polygon, put the 4 corners, and then aggregate them, that you get the time series. Yeah. Okay, any more questions?
I have the same question that I have regarding temperature. You know, like in some fields, maybe we are like applying some irrigation treatment,
Yes.
and then so we have different polygon we wanted to upload. See that.
Okay, let's see options, because I know there is a geemap notebook for shapefiles, custom shapefiles, and converting them into Google Earth Engine features. So that's one thing that you already tried.
Yeah, I tried, but the point is that I don't know why it doesn't show that.
Ah, doesn't show the map. Okay, we can check. Okay, because here when we have the individual features, we could use say add layer.
I tried.
Okay. Well, let me conclude this and we can look at that. All right, you made it. You can now do time series. Fun? Fun. You can evaluate any bit. You can, for example, instead of passing temperature, here, for example, I say, now let's go to the time series here. Here, instead of saying, give me the vegetation index, I can say, give me the red, green, and blue bands. And I can see how every band changes over time. I could say red band, infrared band, shortwave band. So I could compare, I could say NDVI, red band, infrared, shortwave, and see how NDVI behaves along spectral bands. So to have a clearer idea, okay, if the NDVI is high, red should be low and my near infrared should be high. And you can see how these two changes. And we can do that quick change here. You can say red is band 3. And this is band red is no band. Red is band 4, band 5. Got it. Hey, you have to run fast. Okay. Replace the 99. Oh yeah. No, band 4, band 5. Okay. Let me see how that look like. And DBI is the blue line. Band 4, the red, is the orange. The near infrared is the green one. So the DBI that we calculate, you see that we have low values. Look. Yeah, every time we harvest, the red goes up, the near infrared goes down. But every time the plant is growing, the red goes down and the near infrared goes up, up, up. So we can see the behavior of the in every band with this technique, and you just need to do a few modifications to your code. That's good. All right, that's it for today. Thank you for your time. I'll think about of an interesting place for you to do your homework. Probably Texas. Okay. We want a place that has less clouds. Okay, Utah. We tried. There's still clouds there. All right. All right. Also, if you have questions for your projects, we can start covering it now. But thank you again. Thank you.